Hello dolphins, and welcome to the first wave flip notes with Miss Aquad. Before we begin, just a few reminders about flip notes. Number 1, you can always pause the video if I'm going too fast. Number 2, you can replay the whole video or only parts that you didn't understand. Number 3, write down any questions you have on the side to ask me in class later on. And number 4, you must watch the entire video until the end. There will be information needed throughout the video, including possible questions or statements you need to write down. The first word we're going to cover in this unit is wave, obviously, because this is the wave unit. A wave is caused by a disturbance. This disturbance transfers energy from one place to another without transferring matter. Think about it like this. You're at a pool and there's a beach ball in the middle of the pool. All of a sudden, a wave starts to move the beach ball up and down. The beach ball does not move towards the edges. It stays in the center and it just bounces up and down. That just proves that waves transfer energy, not matter. Now, here's another explanation. Think about a serene pond that is still. If someone drops a rock in the middle, it disturbs the still water and the waves are formed. So if you take a look down at the bottom, there's a picture of serene water that was basically disturbed by a rock. Obviously, you see that it forms waves. Next to that picture is an actual transverse wave. In the next few slides, you'll actually learn what a transverse wave is and how to label it. The next word is medium. Some of the waves that we're going to learn about actually require a medium. And then there are going to be some waves that we learn about that don't need a medium. But first, we need to know what is a medium. A medium is any substance that a wave moves through. So let's think about the pond that we talked about in the previous slide. In that pond, what is the medium? What is the wave moving in? It is moving in water. Therefore, the water is the medium. In the second picture here on this slide, you have a seismic wave. A seismic wave is just a big word to represent earthquakes. So in an earthquake wave, what is the medium? It is basically anything that the wave moves through, such as rocks, dirt, buildings, roads. Anything that wave moves through is a medium. Moving on to our next slide. In our next slide, we're going to talk about the two types of waves. The two types of waves are mechanical waves and electromagnetic waves, also known as EM waves. And these are not to be confused with the two wave movements, which we will also be talking about in the next few slides. So in the next slides, we will actually learn about all of these in detail. Let's talk about our first type of wave. The first type of wave we're going to talk about is a mechanical wave. Mechanical waves have to have a medium. These are the waves that actually have to travel through something. So let's talk about this. Matter is anything that is made up of atoms. A mechanical wave moves energy through the matter or the medium, but does not actually move the medium. Just like we talked about in the previous slide with the beach ball being in the water and just moving up and down, it's not really being moved around by the wave. It's just kind of going up and down. Now, an example of a mechanical wave is a sound wave. You can often hear things happening in the classroom next to us, even though there is a wall in between us. Well, what is that wall? That wall is a medium, okay? Other mechanical waves that we have are rope waves. Can you think of another mechanical wave? I want you to write one more mechanical wave example in your notes. Let's talk about the second type of wave. The second type of wave is the electromagnetic wave, also known as an EM wave. The EM waves transfer energy through a field or empty space. What does that mean? That means that this wave does not need a medium. However, it can travel through a medium if needed. EM waves do not give away their energy to the medium. Therefore, they can travel forever. That is why we see the sun's light, because light can travel forever. The spectrum is a diagram of 7 different types of EM waves. If you take a look at the picture below, you'll actually see the EM spectrum. It goes radio waves, microwave, infrared, visible light, ultraviolet, X-rays, and gamma. By the end of this unit, you will know these 7 waves and how they move. Now let's compare and contrast the 2 types of waves. Let's start with mechanical waves. Mechanical waves have 4 things that are important about it. Number 1, it needs a medium. Number 2, it cannot travel forever. Number 3, it can move as a transverse wave or a longitudinal/compressional wave. I know you don't know what that means yet, but we're going to get into those in the next slides. Basically, these are the wave movements, and we'll talk more about those soon. And last but not least, we have several types of mechanical waves. We have sound waves, we have water waves, we have rope waves, we have slinky waves. So there are several different types of mechanical waves. The electromagnetic wave does not need a medium. It can travel forever. It only travels in a transverse fashion, which is different from mechanical wave, which can be transverse or compressional/longitudinal. And an electromagnetic wave, we only have 7. If it's not one of those 7, it is not an EM wave. And pretty soon, like I said, you will memorize those things. Radio waves, microwave, infrared, visible light, ultraviolet, X-rays, and gamma. We are now going to talk about the 2 wave movements. There are 2 wave movements. The first one is longitudinal, also known as compressional. You may use either one of these words to explain the movement. As you can see, right under the word longitudinal, there are 2 longitudinal waves. It looks a lot like a slinky going back and forth. That's basically what a longitudinal wave is. It's just a wave that goes back and forth. The next one is a transverse wave. A transverse wave actually goes perpendicular or up and down. So if you take a look above the word transverse, you'll see a transverse wave. Let's now talk about transverse wave in details. We said that transverse wave is a movement. It basically moves up and down or perpendicular to the direction in which the wave travels. There are 2 types of waves, mechanical and electromagnetic. Mechanical waves need a medium. Well, what mechanical waves move in a transverse fashion? Rope waves, the human waves found at sporting events, actual waves in the ocean. These are all mechanical transverse waves. The other type that we talked about was electromagnetic. All 7 electromagnetic waves move in a transverse fashion. Therefore, how do electromagnetic waves move? Transverse fashion. Do all mechanical waves move in a transverse fashion? No. But do all electromagnetic waves move in a transverse fashion? Yes. Now let's talk about the parts of a transverse wave. The easiest part of a transverse wave is the crest. The crest is the highest point or peak of a wave. The way that I like to remember this is when I look up into the sky, I see a crescent moon. Well, crest, crescent, sounds similar, right? Right. And where do you find a crescent moon? Up in the sky. Therefore, it is the highest point on the wave. The next part that we're going to talk about on a transverse wave is the trough. The trough is the opposite of the crest. If the crest is the highest point, then the trough is the lowest point. The way that I like to remember trough is that most animals eat or drink from a trough. And where is it found? On the ground. So therefore, where do you find the trough? It is the lowest point of the wave. In this slide, you'll see an awesome picture of 2 transverse waves. On these 2 transverse waves, we have the crests and the troughs labeled. I just wanted you to see what they really look like. Now that we've learned the parts of a transverse wave, the next 2 things that we're going to talk about are the properties of a transverse wave. The first property we're going to talk about is amplitude. Amplitude is the distance between a crest or a trough of the wave and the line through the center of the wave. The line through the center of the wave is called a resting point or resting position. So you will hear me saying both of those terms. If I say resting point or resting position, it just means the line through the middle of a transverse wave. So where is the amplitude? The amplitude is normally from the middle to the top of the crest or the middle to the bottom of the trough. The amplitude is not all the way through the wave. So do not draw an amplitude going from the top to the very bottom, because if you do that, that is incorrect, and I will count it wrong on your test. So make sure you know amplitude is from the line to the top or the line to the middle. So from the middle. The second transverse property we're going to talk about is wavelength. Remember, properties are characteristics. So the next characteristics we're going to talk about is a wavelength. What is a wavelength? It's the distance from one wave crest to the next crest, or from one trough to the next trough. Now, you can do crest to crest or trough to trough, but you cannot do from crest to trough or trough to crest. So you have to choose one or the other in order to complete this property. Now let's move on to the second wave movement. The second wave movement that we're going to be talking about is a longitudinal/compressional wave. You will hear me say both of these words, so either one is fine. Let's talk about what it is. It's basically a type of wave in which the disturbance moves in the same direction as the wave. That just means that it goes back and forth. Well, what are compressional or longitudinal waves caused by? They are caused by a disturbance, but normally it's caused by a vibration, which is the disturbance that causes these. So therefore, what are some examples of a longitudinal or compressional wave? Some examples are sound waves, slinky, your P waves in an earthquake, and we'll talk more about that as we get into geology, but that's just a great example of a longitudinal wave. Something unique about longitudinal waves is they can only be mechanical waves. That means that they have to have a medium, unlike transverse waves. Transverse waves can be mechanical or they can be electromagnetic, depending on what they are traveling through. Now that we've learned about a compressional/longitudinal wave, let's talk about the parts of a compressional/longitudinal wave. Basically, let's start with compressions. Compression is a region of increased pressure, the area where the wave is compressed or pushed together. If you take a look at the pictures below, do you see where the dots are really pushed together or tight together? That's called a compression. If you look at the slinky, the area of the slinky that is pressed together, that is called a compression. So areas that are extremely close together are compressed. That's called a compression. The next part of a compressional or longitudinal wave that we're going to talk about is a rarefaction. It is the opposite of a compression. In a compression, we said it was pushed together. In a rarefaction, these are areas that have decreased pressure, and they are actually areas that are spread apart. So if you take a look at the green word, compression, that arrow represents the area that is compressed. That's the compression. If you take a look at the black word that says rarefaction, and you see the black arrow is pointing at the area of the slinky that is basically spread apart. That is your rarefaction. You need to know how to label these. Make sure you understand it and know how to label these. Just like transverse waves, longitudinal waves also have properties. Well, one of the properties of a longitudinal wave is the same as the property of a transverse wave, which is amplitude. However, in a longitudinal wave, the amplitude is a little bit different in the fact that it shows how compressed the compression of a longitudinal wave is. So if you take a look at the pictures below, you actually have two pictures. We're going to start off with the one with the pitchfork. As you can see, the dots are a little bit more, the compression have dots that are a little bit more spread out. That is less amplitude because of the fact that it's not as tight together. If you take a look at the one underneath it, the dots are closer together. They are more compressed. So the more compressed it is, the higher the amplitude. The less compressed it is, the lower the amplitude. Now if you take a look at the picture to the right, again, it's the same type of thing. There you see the black dots are not very compressed together. Therefore, you have a low amplitude, less compression, less energy. The one beneath it, the dots are very close together. Therefore, it has a greater amplitude, meaning that it has greater compression, higher pressure, and more energy. The second property of a longitudinal wave or compressional wave is wavelength. Just like the wavelength in a transverse wave, the wavelength in a longitudinal or compressional wave is basically from one compression to the next compression, or one rarefaction to the next rarefaction, which is very similar to transverse wave where they did crest to crest and trough to trough. So again, you have to choose one. You can't use both. You either use compression to compression or rarefaction to rarefaction, and that's how you find wavelength. The next property that we're going to talk about is frequency. Frequency is actually used for both transverse and longitudinal wave movements. What is frequency? Frequency is basically the number of waves that pass a fixed point in a given amount of time. Usually it's about 1 second. So let's try to figure out what is the frequency for the two waves that we have. Let's start with the transverse wave. We have one of high frequency and one with low frequency. So if we're looking at the number of waves, we actually have to count the wavelength. So let's take a look at the first one. High frequency, 1, 2, 3, 4, 5 wavelengths. If I'm looking from crest to crest or trough to trough, I get 5 wavelengths. Therefore, what is the frequency for the high frequency transverse wave? 5. Let's now take a look at the low frequency wave. If you take a look at the low frequency wave, again, you look from crest to crest or trough to trough. So the first one, 1, 2. So low frequency is 2. Now let's take a look at a compressional or longitudinal wave. Again, this time instead of looking at crest, because longitudinal waves don't have crest, they have compressions and rarefactions. You can choose to either do compression to compression or rarefaction to rarefaction. So let's take a look at the first one. Let's look at the high frequency. You go 1, 2, 3, 4. So what is it? 4. Let's take a look now at the low frequency for the longitudinal wave. You have 1 and you have 2. So what is the frequency for the low frequency longitudinal wave? It's 2. I hope you enjoyed the slides and I hope you've learned something. What's next? Now that you've finished the notes, what you're going to do next is you're going to complete 2 tasks. Number 1, you're going to watch an interactive video on Discovery Education. Below is how you log into Discovery Education. I will show you this in class so that you know where to go exactly, but just in case you forget, it is on these notes as well. You're going to go to Discovery Education. Your username is WCP, and then your lunch number, your password is the lunch number. Once you have completed the video, you're going to create either a 2D model or a 3D model of the 2 wave movements. That's the transverse wave and the longitudinal/compressional wave. You must make sure to label the parts and the properties. Please make sure to label the parts and the properties. All right, and that is due on Monday.